start the recording. It's a pleasure to welcome today Devarshi Mukherjee, who from Göttingen University, whom we hope to have here next year as a Fyodor Lenin scholar here in Buenos Aires. And today he's going to talk about the analytic Hochschild constant Rosenberg theorem. Please go ahead, Dave.
Thanks for the introduction, and yeah, hope to be there soon. So today I'll be talking about a version of Hochschild constant Rosenberg theorem. And well, in the course of the talk, I'll explain what's analytic about it, but I will spend considerable amounts of time talking about a sort of a different perspective on the Hochschild constant Rosenberg theorem itself, which is more topological. Okay, and it's joint work with Jack Kelly at Kobi Kremnizer. Okay, so let me start with what I know as the usual Hochschild constant Rosenberg theorem. So there are two sides to this story. You have some geometric object that you want to study, so say a smooth manifold or its algebra of smooth functions. And the two sides are the Hochschild side and the Dram side. And more specifically, if you have a smooth manifold, you can talk about its Dram Chromology, which is a fundamental invariant for smooth manifolds. And this is defined as the homology of a certain cochain complex that you see. So the cochain complex is defined in terms of the algebra in degree 0 and the differential forms in each other degree. Or alternatively, you can study the Hochschild homology of the algebra. And this is defined as the homology of this cochain complex given explicitly as you see it. And there is a certain decoration on the tensor product. This is a certain technical subtlety. It only really works, but for what I'm going to talk, this only really works if you use the completed tensor product. Okay, so you have these two invariants for the algebra of smooth functions on a manifold. And well, since this is a non-commutative seminar, it should be noted that Hochschild homology makes sense for any associative algebra. And it's one of the more fundamental invariants in non-commutative geometry, which is used to define certain other invariants such as cyclic homology and periodic cyclic homology. Okay, right. Now, how are these two invariants related? The classical theorem, which goes back to Hochschild constant Rosenberg, and it states that we have an isomorphism of modules. So if you take each homology of this chain complex that I defined previously, importantly using this completed tensor product, then you get the the differential forms on the manifold. And furthermore, you can then get a statement about periodic cyclic homology. So the periodic cyclic homology of smooth functions on a manifold are given by direct sums of Dram cohomology groups of the manifold. And in this sense, periodic cyclic homology generalizes Dram cohomology and Hochschild homology generalizes differential forms. Okay, so that's what I know of as the classical Hochschild constant Rosenberg theorem. But let's turn to the algebraic versions, because this is kind of the route I'll take to talk about the analytic versions. Okay, so things like differential forms of Dram cohomology can be talked about for any, let's say, smooth commutative algebra, and then any commutative algebra over a commutative ring. So what we need to do in that paradigm is we need to replace differential forms with scalar differentials. And well, it's given by this universal property. So derivations from A to some module M is given by A module maps from omega 1 to M, and this object omega 1 kind of uniquely characterizes this isomorphism that you see. But well, you can define this very explicitly as, let me annotate. So if you never saw this previously explicitly, then this is given by, well, it's the A module generated by symbols of this form where D satisfies the Leibniz rule. Okay, and then you can define higher Hkr differentials by taking exterior powers of this. So in particular, that's given by things of this form. Okay, and that again defines a certain cochain complex precisely as with a smooth manifold case. And the algebraic Dram Chromology of some commutative algebra is given as it's defined by the homology of this cochain complex. Okay, and the similar statement then holds even in this algebraic setting. So if you have a smooth commutative algebra, then there is an isomorphism of A modules given by the Hochschild homology modules and the modules of Hkr differentials. And furthermore, if the field, well, if the ring has characteristic 0, that is, if it contains the rationals, then the periodic cyclic homology is again given by direct sums of Dram Chromology groups. And like a remark is that this proof is kind of by hand. You use what is called the anti-symmetrization map to prove this isomorphism. And then you use some formal machinery about mixed complexes to show that this isomorphism holds for periodic cyclic homology. Okay, now the story gets a bit more complicated, where if we have statements about the Hochschild homology complex and the Dram Chromology algebra, and by that I mean the commutative differential graded algebra of differential forms. So in general, there is no information about what happens at the level of complexes. And more so if you include the additional structures that Hochschild homology or the Hochschild complex and the Dram complex, if you include these additional structures, then it's unclear what happens between two sides. And well, in what follows, I'll talk about what these additional structures are and how they are precisely related. Okay, so that's basically the problem at hand, and it's been answered in several different stages, I think over the past 2 years in the algebraic setting, and of course, we'd like to extend it to the analytic setting. Okay, so let's start with a slightly different point of view on Hochschild homology. And from now on, all my algebras will be commutative, although the invariant itself is defined for non-commutative things. But let's stick to the commutative side for now. Okay, so if we have a commutative K algebra, where K for now is just any ring, then the Hochschild complex that you saw previously, this is a simplicial commutative algebra. So if you know, there is something called the Dold-Kahn correspondence, which relates positively graded complexes with simplicial objects. And now if you additionally know that the algebra is commutative, then the phase and degeneracy maps are algebra homomorphisms, and this turns the Hochschild complex into a simplicial commutative K algebra. Okay, now let's just denote this category of simplicial commutative algebras by this. Okay, now the next thing is, well, moving on, what I spoke about previously when I defined this explicit chain complex that computes Hochschild homology. There's a slightly different way of writing this. You can define what is called a bar complex. And this is a certain projective resolution of the algebra you start with by A tensor A modules or A bimodules. And it turns out that that other complex which I had defined, that's given by this bar resolution tensor with A over A tensor A. So this is an explicit thing which can be checked degree-wise.
A little, well, one little question. So the Hochschild complex you regard it as a simplicial commutative algebra with a shuffle product, I imagine. I don't recall, but is BA, the bar complex also has a shuffle, doesn't it?
Yeah.
Okay, and this I mean, this isomorphism that you write there upon tensoring, I mean, is this an identity, an isomorphism in the category of simplicial commutative algebras?
I don't think the multiplicative structure carries over. I think this is just at the level of, this is on the nose really. So this is for each term in the complex that's isomorphic.
But I mean, BA maps onto HH.
Yeah.
Isn't that you say that is not a homomorphism of simplicial algebras?
Yeah, I don't think it is. Not of algebras.
Okay. Okay.
Yeah. Right. Okay. So what is true is that because this is a projective resolution, this Hochschild homology complex, in a sense, models the derived tensor product. So this derived tensor product is computed by taking any projective resolution of A here or here, doesn't matter. And well, this is just a different way of writing this thing, which we use later.
But then, then, I mean, so the identity above is occurs in the category of simplicial modules over BA, say. And in that sense, I should understand the derived tensor product.
Yeah.
In the category of simplicial modules over A tensor A.
Yeah.
But then you say the isomorphism is in simplicial algebra. So the derived tensor product is not derived in the sense of the category of simplicial commutative algebras with some model structure, but in that of modules.
Yeah.
Okay.
Okay. Right. So now let's talk about. Okay. So well, just remember this identity. We'll come back to it somewhat later in the thing. Right. Now we want to understand, as I mentioned, there is some additional structure. The one additional structure that we know of is that we can view HH of A when A is commutative as an object of simplicial commutative K algebras. Now another structure that it has is that it has an S1 action, so an action of a circle. Okay, and it would be a good idea, I guess, to recall how this precisely works. Okay, so let's denote the category of commutative K algebras by this. Then we can define what is, define what is called a cyclic category. This has the same objects as a simplex category, but it has some additional relations, and the automorphisms between any two ordinals is given by the cyclic group. So I won't really write down what the relations are, kind of hard to remember them. And a cyclic object is a functor from this cyclic category to, it's a contravariant functor from the cyclic category to a given category. And recall that a simplicial object is just a functor from delta op to this category. So this is a slight refinement of this. And what's shown classically is that Hochschild homology is a cyclic object inside this category. And furthermore, it's initial for cyclic objects that come with a morphism from A to this object that you start with.
Sorry, the homology, not the complex.
Oh, okay, yeah. So I really mean, so when I say Hochschild homology from now, I just mean the Hochschild homology complex. Yeah. So not the homology groups. Yeah. So Hochschild homology complex. Okay. So classically, it's in the book of Lode. We can show that this is kind of initial for cyclic objects, and particularly it is also a cyclic object. Okay. So now we know a second additional structure that it has. So this belongs to this functor category and from cyclic category to commutative hierarchies. Okay. So what we now like to talk about, as I was explaining, we want to speak about an S1 action on this Hochschild homology complex. Were you asking something?
No. When this feature that you have to write on top of the thing, it does not erase any of what you write. So I still can see the omega 1 A over K, the A0 D A1 D A.
Yeah, I see. It doesn't.
Then they are all,
I see.
Successive layers of.
Okay. Well, I'm not writing anything very significant as yet, but I'll get to that. Okay. Anyway, right. So now we know that HH is a cyclic object. Okay. So now what's the relationship between that and S1? The first thing is we can view S1 as a category with one object and whose morphisms are elements of S1. And a functor from S1 to a category, just by definition, is equivalent to an object with an S1 action. Okay. Now, there is a certain construction called the nerve construction. So you can apply the nerve to any category. This gives you an infinity category. And the nerve construction is fully faithful. So if you have a functor from S1 to any category, you can apply the nerve. And this gives you an infinity functor, which for now is just a morphism of simplicial sets, which goes from the nerve of S1 to the nerve of C. Now, the only thing that we note here is that this is some infinity category. And essentially, we'd like to replace, we want to plug in some infinity category we care about, such as spectra or the category of complexes of K modules. Okay. And this is how we'd like to define what it means for a complex to have an S1 action. And that's exactly how we define it. So if we take any infinity category with this as the kind of background, if you take any infinity category, an object of M with an S1 action is an infinity functor from BS1 to N, where BS1 is the classifying space of S1. Okay.
Sorry, you regard this one as a discrete group?
Yes.
Okay.
Okay, and now the kind of black box result is that the nerve of concyclic category, when we take the geometric realization of that, what we get is a model for the classifying space of S1. So this is some classical result. Let me erase things. Okay. And furthermore, what we use is that the singular complex functor and the geometric realization functor are in a junction. So this gives us a map from the nerve of the cyclic category to the classifying space of S1. So in other words, if we start with some functor like this, then by restriction, we get a functor from the nerve of the cyclic category to N. And as we know, this is the classifying space of S1. Okay, and conversely, if we have a functor x, and furthermore, if M admits geometric realizations, so for chain complexes of modules or spectra, then it admits geometric realizations. Left adjoint functor to, well, this assignment. And this just takes a geometric realization of such a functor. And this gives us a functor from BS1 to M. So in other words, whenever we start with a functor from here to here, we can geometrically realize it and get a functor from BS1 to M. And well, this is like the crucial ingredient. So in this sense, we can always get an S1 action if we start with, let's say, this Hochschild complex. Okay. And well, what we do there is we take the bar construction, so we take the bar resolution, we take its geometric realization by this machinery that I talked about, and this gives us a functor from BS1 to M. So in this sense, we can view the Hochschild complex as an object inside simplicial commutative algebras. And now we have this additional enrichment of an S1 action. Okay. Right, so just to repeat, what we're doing is we started with this chain complex, which was positively graded, so it's a simplicial module. But furthermore, if we talk about commutative things, then this is simplicial commutative algebra. And what I've now done is I've showed that it comes from an S1 action canonically. Okay. Right. Okay. Again. Okay, well, let's just write this guy here. So the latest is that this is inside this category. So simplicial commutative K algebra with an S1 action. Okay, but for what I'll do next, I kind of want to represent this functor category, that is functors from BS1 to simplicial commutative algebras in a slightly different way. Now, if you know this statement from, say, representation theory, then you know that group actions on some module is the same thing as module actions over the group. Okay, so let's see what that means in this context. So let's take the group ring over S1. Well, this can be kind of given by this, well, okay, you can disregard this statement. It's just the group ring over S1. And it is also a bi-algebra, which will be relevant in a bit. Now, what we have is, just by this kind of statement that we know from representation theory, if we have group actions on something, then that's the same thing as module action over the group ring. So in this sense, we can view this Hochschild homology as something sitting inside this category. Well, let me just take chain complexes of K modules for now. So, well, this thing will kind of change in a very crucial way, but it is still sitting inside simplicial modules, but well, it will change shortly. Okay, and as I said, this point of view is kind of relevant when we bring in filtrations. Okay, now, what do we mean by filtrations? Okay, well, we kind of don't need to bring in filtrations if we stick within the realm of positive, well, zero characteristic. But it turns out that things get far more complicated and intricate if we want to work either integrally or in positive characteristic. As I remarked at the start, to prove that HP gives you the Dram Chromology, you kind of needed to use that your field contains the rationals, you need to divide some n factorial or whatever. Now, in positive characteristic, there is a similar statement which still holds, but this only holds at the level of filtrations. And well, kind of the precise statement is that if you have a smooth FP algebra, then HP admits a filtration whose associated gradient gives you Dram Chromology. So the nth associated gradient gives you the Dram Chromology. Okay. And if you plug in,
I mean, this is the Rham cohomology. I mean, so for example, if A is, say, a polynomial ring, it's a lot of garbage equal to a lot of garbage, right? I mean,
yes.
So it's there is no homotopy invariance anywhere.
There's no homotopy invariance.
I know. I mean, these are very important people who have worked in this, but I never understood what's the interest of studying the Rham cohomology. I mean, not a homotopy invariant version of the Rham cohomology, but just the Rham cohomology. In characteristic P, we has all these. I mean, do you have a motivation for considering that?
Well, I don't, but I mean, it gives you crystalline cohomology, which is not a homotopy invariant theory. So you have all sorts of strange things that happen. And even in the simplest cases, you get infinitely generated things. You get the polynomial ring rather than just FP. But I guess the motivation kind of comes from arithmetic geometry. So I have no idea what the motivation for these guys were. As well, what we do is we do rigid cohomology. There is homotopy invariant, but these things are not, and neither is the topological periodic cyclic homology. So yeah, I don't know what their precise motivation is. So I guess it's important for like number theory and all
that. Okay.
Yeah. Anyway, so for this purpose, all I'm saying is that you have a statement like the Hochschild and Rosenberg theorem's computation for periodic cyclic homology. It's just that you get a statement at the level of filtrations. So there is a filtration on HP or DP, whose associated gradient gives you Dram cohomology groups. Okay. Right. Okay, now let's work in this category of complexes again. For any category, you can define the category, the filtered infinity category or filtered category. This is just given by functors from the category of integers to the target category. And for some terminology, a filtration on a complex is called complete if its limit is 0.
Sorry, a func. So how do you consider Z as a category? As an order set, as a group?
Yeah, as a periodic set. Yeah.
Okay. Okay.
Yeah. Okay, and well, given a chain complex such as Hochschild homology, you can always define a canonical filtration. It's called the Postnikov filtration. So this takes you from a chain complex to a filtered chain complex. I guess I could write down what this Postnikov filtration is in case you want to know. So if you take some chain complex X, then this is given by where each tau n So this is a complex. So for I, you get 0 if I is less than n. This is the co-kernel of xi plus 1 to xi. If I is n, and it's xn if I is greater than that. Okay, so this is a certain filtration. And in particular, when you plug in the Hochschild homology complex, the resulting filtration is called the HKR filtration. Okay, so in this sense, this tau of HH, this is a filtered simplicial commutative algebra. And furthermore, it has an action of what is called the filtered circle. So this was some new terminology that was introduced a year ago. So this is now something which is, previously HH was sitting inside S1, simplicial commutative algebra. But this tau of HH is now sitting inside this linearized circle, because we don't want to view this as BS1 to commutative algebras, but rather this linearized version. So this is now sitting inside something like this.
A little question.
I'm giving heavy invitation.
Does
yeah.
I mean, the Hochschild complex always carries a filtration that in characteristic 0 splits.
Yeah.
And it's related to this Euler idempotence that Lode talks about. So does this type of filtration not play any role here? Because the filtration that you wrote is, I mean, one that you can define for any complex and is related to truncations, not very meaningful. So that
yeah. So if you work integrally, they don't split any longer. So that's when the filtration.
Yeah. I know. There is a filtration, but that's not the truncation, the canonical truncations that you have.
Yeah.
It's a different filtration, or isn't it?
Which one? So I'm only talking about this Postnikov filtration.
Okay, which comes from truncations.
Right.
That you can define for any complex. So my question is whether this other filtration, the meaningful one, the Hodge filtration, if you will, plays any role here, because you are not using it so far.
The Hodge filtration comes in later. It does come in later. Yeah. Okay, so at the moment, I'm just viewing this as a filtered simplicial commutative algebra with an action of a filtered circle. Okay, now, as I described previously, the usual Hochschild complex, it came with a certain universal property. It was initial for, so if you had a map from here to any simplicial object, then this always extended uniquely to a map from the Hochschild complex to that. And a similar universal property also holds for the Hochschild, for this filtered Hochschild complex. So this HKR filtration, which comes from this truncation, this is the initial one with the action of the filtered circle. Okay, now there is this category that I've mentioned over here, this category of filtered simplicial commutative rings with a filtered circle action. There is some technicality that goes on in defining precisely what this category is. Okay, so how does this go exactly without getting into too many details? So this thing is sitting inside T modules over into chain complexes of R modules. Now, this thing is a Hopf algebra, so it has this, it's a bicommutative algebra, so we can take it, it's also dualizable. So this is the same thing as co-modules inside the dual of it.
But what is this thing? This thing is a Hopf algebra. Which thing?
T.
T.
Yeah.
Because it's a group ring.
It's a group ring, yeah.
Yeah, okay.
Okay, so this is the same thing as co-modules of a dual algebra. And okay, now we want to bring in filtrations. This is, there's nothing interesting going on here. Now, the way to do this is using well, it's a theory that's being kind of developed by these names that I previously showed. And it's called the theory of polynomial functors. So what you want to do in this is you want to enlarge simplicial commutative algebras to include non-connective objects. And the reason for this is that this thing is not a connective object. So you can't do this naively. You can't just put in simplicial commutative R algebras here because this is non-connective and this only has connective things. So you kind of enlarge this to what are called derived commutative R algebras. So just to get a feel for what these objects are, any derived commutative R algebra has an underlying E infinity R algebra. So that is a commutative algebra object in the category of complexes. Right. And now if you take some
a commutative algebra object in the category of complexes is the same as a differential graded algebra, isn't it? Okay.
Okay. So now, well, now we can define everything in a sort of compatible way. So now you have, if you start with some derived commutative R algebra, then this HH of A is a co-module inside this dual object inside the category of derived algebras. And now when you bring in filtrations, things still make sense. So this is now sitting inside co-modules inside the filtered dual circle algebra inside the filtered derived commutative algebra. And this is exactly what this category is, but we need to do this extension to derived commutative algebras. Okay, but anyway, the take home is that this HH with the filtration, it satisfies a universal property which is analogous to this one. Oops. Okay. Okay. So now it got zoomed out. Just a second. Oops. Okay, sorry about that. Oh, can I just share again? Okay.
Somehow it was taken by the G bars. I mean, they were. What happened that made them so small?
I don't know.
The 150% up there.
Okay, maybe make it 200. Is this better now?
A little bit bigger, it will be better.
300.
Yeah, that's more like it.
Maybe you can use fill to fill the page or something like that.
Page fill, yeah.
They are on the 300%. You have that option also.
I see.
No, on the 300%.
On the that's right.
300%.
That's fine.
Ah, yeah, yeah.
Great. Okay. Anyway, so back to this take-home message that this filtered HKR, this satisfies a universal property. It is initial in the category of filtered simplicial commutative rings with a filtered circle action. Okay. Now let's come to Dram Chromology, and this is where this Hkr filtration comes in. Okay, so the Dram Chromology, now I talk about it again, I don't want to talk about the chromology groups, but the complex itself. Now this has again a canonical filtration by subcomplexes. And now if A is a simplicial commutative algebra, we can talk about a derived version of Dram Chromology. And this is done by taking Kahn extensions of Hkr differentials. And this gives you cotangent complexes or its derived exterior powers. So this defines derived Dram Chromology. And this also inherits a filtration.
So the LIs are simplicial objects.
Yes.
Okay.
Yes. Right. Okay. Now we get a filtration also on this derived Dram Chromology, but it's not yet complete, so we need to complete in this filtration. Okay. And once we complete in this filtration, we again get derived algebra in the sense that I spoke about previously. Okay. But well, it's more than just a derived algebra. It's now a complete and filtered derived algebra. Okay, now let's go from filtered to graded algebras. And there's a way to do that. It's called taking the associated graded functor. So this just takes filtered objects and takes its subquotients. Okay, and as I mentioned, there was this T-fill. This was the Postnikov filtration applied to the group algebra with a circle. Now, if we take the associated graded of that, we get some graded algebra. Okay. Now, there is a general result called Koszul duality, which relates complete and filtered objects with graded objects. Now, in our context, this would mean an equivalence between, well, wherever this derived Dram complex with its completed Hkr filtration, this was sitting in this filtered side. We can now use this equivalence to view it as a graded object. And this graded object now comes with this action of T plus. Right.
So you can recover I mean, of course, I mean, this is very abstract, and I'm not sure, I'm sure I'm not following the details, but I mean, my intuition is that you usually cannot recover an object, a filtered object, from the associated graded. You lose information, but even if you complete, unless, I mean, the completion is somehow split in a sense. So how does this work, that the completed filtered objects are the same as graded objects? That sounds counterintuitive. How would you explain this?
Well, I mean, I'd have to get into too many details which I can't say off the top of my head right now, but it is it's a statement I picked up from about 15 pages of proof. So it is true, and I can tell you about it after this talk. Right now, we're running a bit short time. But I guess the result holds in any Z linear stable infinity category. It certainly holds in this context. I don't know how generally true the result is, but this Koszul duality is well known, at least in this context. Okay. Right. Also, and secondly, just to add, the applications that I'll talk about in a bit will only be over characteristic 0. So it's not too suspicious in that realm anyway. Okay, now, as I was saying, this Dram algebra with all its additional filtration structure, we can now view it as this graded object with this D plus action. And this D plus action, just intuitively, this encodes for the shift in the Rham-differential. So this is a higher algebra way of talking about a coherent co-chain complex. So if you remember, if you have a CDGA, that is a commutative algebra object inside chain complexes, you have a grading and you have a differential, and these are compatible. This category has precisely these as its objects. So it has a grading and it has this differential, and these are compatible in this higher algebraic way. Okay, so in a sense, it's just CDGA type of objects. Okay, and similar to the filtered Hochschild homology case, if you work in this derived setting, if you have a derived algebra, then this the derived Dram Chromology is initial for maps from A to this x0, where x0 is really the 0th part of some non-negative derived algebra. So again, this non-negative comes from the fact that everything that's going on has no negative homotopy. Okay, so again, the model is that you have the Hochschild side and the Dram side, and they're both initial in the respective categories. Okay, and then to kind of summarize this, this associated graded functor, it kind of induces a functor on these two categories that I talked about. And then, the actual HKR theorem, this very generalized HKR theorem, states that there is a commuting diagram of junctions. And in fact, these HH and this derived Dram complex are kind of defined by the junctions. It's defined by, there is a functor going from this mod D plus D alg or filtered S1 simplicial. You basically forget all your structure and just get something simplicial. And this is the left adjoint to that functor. And similarly, this is the left adjoint to the functor that forgets everything over here. And then this diagram commutes. So in other words, the associated graded of the Hochschild algebra on some simplicial commutative algebra gives you the same thing as the derived Dram algebra.
So, and here you're not assuming, you said, I think if I understood correctly, that in the applications you were going to assume characteristic 0 or something.
Right, in the analytic applications, which I'm going to talk about.
But not here, but not here.
This holds integrally, that's right.
So it does not say, so this, let me see, the usual statement that you can find in Lodé's book is that Hochschild homology, Hochschild complex splits in a sum of complexes, each of which has the derived type of Li of omega.
Mm-hmm. Yeah.
But this splitting needs characteristic 0.
That's right. Yeah.
But you always have the filtration.
Yes.
But here, yeah, so the only disturbing thing that I find is the gr there, because it would mean that you still have the splitting, which is okay. Anyway, there is some categorical context in which that makes sense.
Right, exactly.
Fine.
Okay, now this derived algebra, so this is kind of where our project starts, although I'm kind of running short of time. But anyway, I think I have like 10 minutes. Anyway, So this notion of derived algebras, one can replace this with what is called a derived algebraic context. So again, this is a way of formalizing how you get non-connective things from simplicial things. There's a precise way this can be defined. So derived algebraic context is a stable, presentable, symmetric, monoidal infinity category with a T structure, which you might know from triangulated category language, and a small full subcategory contained inside the heart of this T structure. And this is subject to certain axioms, of which I think the most important one is that there has to be a set of compact projective generators for the C0. Okay, so that's a derived algebraic context. And in any such derived algebraic context, one can talk about a derived commutative algebra object. And in any such, and for any such derived commutative algebra object, you can again define things like Hochschild homology. You can talk about derived Dram Chromology, and you still have this commuting diagram of adjunctions, even if you replace derived algebras over R by any derived algebra object inside some derived algebraic context. Okay. Right, so the example which kind of makes things a bit concrete, in the algebraic setting, the derived algebraic context that's being talked about is the category of chain complexes of modules. The positive part of the T structure is given by complexes which have vanishing cohomology in negative degrees. And similarly, you can talk about the negative part of the T structure. And the heart is given by just the category of abelian groups. And this C0 is just given by free objects in this category. Okay. Now, this is the initial derived algebraic context, in fact. Okay, and okay, since it's initial, if you can find some other derived algebraic context, then we can use this to bootstrap arguments from this context to other derived algebraic contexts. Okay, so the derived algebraic context that we use, or we care about, is the derived algebraic context of complexes over complete bornological modules. If you don't know what bornologies are, then you can also take the larger category of inductive systems of Banach spaces. Now, there's some analytical technicality which obviously comes in here. These are not abelian categories, these are quasi-abelian categories. And well, if you have any quasi-abelian category, the thing to note is that if you take what is called the left-D structure, so it is some T structure, which again can be defined similar to this, where instead of having vanishing homology groups, you have complexes which are exact in negative degrees and similarly exact in positive degrees. Okay, so if you have this left T structure on this category, and if you take its heart, so the heart is just the intersection of the two T structures, then that's an abelian category. And in fact, in this case, it's given very concretely by additive functors from this collection to the category of abelian groups, where this collection is given by precisely the projective objects in this category. So that's L1 of X, where X is a set. So these are just summable sequences. Okay, and we spent some time proving that this is a derived algebraic context, so it satisfies all the axioms that are needed. Okay. Now, let's see what this means geometrically. So let's first see what this means geometrically even in the algebraic context. Now, there was this formula that I had written down right at the start, that this HH is given by this derived tensor product. Now, if you plug in geometric things such as let X be the spec of some commutative ring, then you recover this formula. You get the fiber product of over X times X of X. And this defines what is called loop space. So the loop space from topology, if you remember, is just the home of S1 to X. And that kind of puts in perspective why we get something similar if we plug in Hochschild homology. So it's a concrete formula. Now, what does the Dram algebra, what does that give geometrically? That gives the spec of the, well, that gives us the shifted tangent space. So the spec of the Dram algebra gives us the tangent space shifted by -1. Okay, so the HKR theorem says that the space of the free loop space on, let's say, a spec of a ring is the same thing as the tangent space shifted by 1. And then there's some complicated work that can be used to show that you can globalize this. So you can glue together affines to actually get the same statement, not just about schemes, but also stacks. Okay, and in the analytic version, what we want is, we want similar results such as these. So we want the loop space to be the same as the shifted tangent space, where X now could be something like a complex analytic space or a rigid analytic space. Okay, and that's kind of a summary of the results we have. So if you start with a Banach field, other things do hold integrally, at least for this talk, so I don't say anything false. If you do have a Banach field such as complex numbers or QP or the real numbers, then the category of complexes of complete bornological vector spaces over such a field, or inductive systems of Banach spaces over such a field, is a derived algebraic context. And in particular, by this very general result that I spoke about previously, that is with this commuting diagram of adjunctions, the Hochschild-Rosenberg theorem holds. Okay, and the second main thing is that why this is relevant to analytic geometry is that it's also what is called a homotopy algebraic context, which means that it's a symmetric monoidal model category with a long list of axioms. And these axioms enable us to essentially do derived geometry that has nice rules for gluing and so on. There's a nice Toen-Vezzosi topology. So it has all the ingredients that are needed to do geometry relative to a symmetric monoidal category. Okay, so it is a homotopy algebraic context. And using that, we can kind of globalize all these results to actually get the same statement about a complex analytic space, a Berkovich space, a rigid analytic space. And for any such space, we have the loop space is the same as the shifted tangent space. Okay, that's where I'd like to stop.
Okay, thank you very much, Dev. Well, I still have to digest the meaning of this. So if does this tell me anything if I have a bornological algebra or differential grade in bornological algebra about the Hochschild homology or such a thing, whether it decomposes in a certain way, or is there any such? Does this tell me anything in the context of what is in Lodet's book, but for bornological algebras?
Yeah, so you get the same results as in the algebraic context, where you can replace simplicial commutative algebras with simplicial commutative bornological algebras. Yeah. So yeah, that's kind of what I mean by, in particular, the Hochschild-Rosenberg theorem holds. So if you take a simplicial commutative bornological algebra, you take its Hochschild homology, then the Hochschild side is the same as the Dram side, the derived Dram side. Which is not super surprising, but the derived parts has these consequences in derived analytic geometry. That's the kind of the upshot of all this.
So let me see what happened to the participants. Are there any further questions, or shall we stop the recording? Gisela, are you there?
Sorry, I was on. No, I have no questions. Thank you very much for your talk.
Okay, so let me stop this.